go ahead and get into it. So we want to look at 57, file naming. Let's see what it's all about. All right, so we're given an array, and I guess the idea is, imagine this is like in your operating system, Microsoft Windows or OS 10. What do they call it on Mac? Anyway, imagine it's your operating system, and maybe it's Ubuntu. There we go. Point is, we've got some files. We want to name some files here. Maybe these are like Microsoft Word documents, or maybe it's like MS Paint files, like we're doing some PNGs or something like that. But the point is, you probably noticed this. I think the most common occurrence of this is if you try to download something off the internet, and then maybe you forget that you downloaded it already, and you try downloading it again, and this kind of thing happens, right? Like the first time it's called doc, but then the second time it's like, oh, well, there's already something called doc, so this is going to be doc 1. It's just like putting this extra 1 over there. So basically the idea is we want to build something that's going to handle these file names in that kind of way. Imagine we're downloading this file, and then we're downloading this file, and then we're downloading this file. We want to know, well, what are they going to be called locally? So if we try to download doc, we'll assume we start with nothing, right? So it's just going to be regular doc. And then we try to download doc again. Well, okay, now that's going to be doc 1. Try to download image. Haven't seen an image yet, so that's just going to be image. Try to download doc 1. Well, it says, oh, well, there's already a doc 1 here, so I guess we'll make that doc 1 1. Okay, and then after that we try to download doc once again. We basically say, oh, okay, well, there is a doc here, so maybe we'll try doc 1. Oh, no, there's a doc 1 there, so we'll make it doc 2. We'll just increment the index here as much as we need to. Okay, so that's basically the idea. So in formal terms, we're given a bunch of file names in the order of their creation. We know that we can't have 2 files with the same name. And so basically the one that came later, if there are duplicates, should have this k thing where k is the smallest positive integer such that the obtained name is not used yet. Okay, and then we want to return an array of names that will be given to the files. So the actual names that the files will have. Okay, great. So let's try to get that done. So basically, we're going to be returning something like this, right? We're going to have an array of file names, and we want to return that. That's the plan, basically, right? Yeah, I think that's the plan. Okay, so how are we going to do that? Well, basically, we'll go through the list here. So we'll do a for loop, and I don't think it's really that important for it to know what index the name is at. So it's just going to go through and get each name. So we'll just say let name of names. Since we don't need to know where it appears in the original names array. We don't need to know which index this thing was. And the reason we don't need to know that is because it doesn't matter necessarily where these things were. It's more what's in the actual array of file names already. That's what we want to be paying attention to. Okay, so basically the idea is we'll say, well, since it depends on whether or not file names already includes this one, we'll say, well, does it include this one? If file names dot includes name, then we're going to do one thing. Otherwise, if it doesn't include it, then we'll do a different thing. Specifically, I think it's easier to think about what we're going to do if it doesn't already include that file name. We're just going to say file names dot push name. Let's just put it in there, right? If it's not in there already, we'll put it in there, no problem. Okay, so then what's the other situation here? Well, if it already includes that name, then basically we'll say, okay, so let's say what do we want to call this? Index? Do we call it index? Maybe instances, something like that. So we'll say let instances be assigned the value of 1. And that's sort of like our way of saying, oh, okay, well, there's already one instance of this name. And then we basically want to check, okay, I guess I'll call this new name. Yeah, new name. And it's basically just going to be name plus well, okay, yeah, we want to put the number in parentheses here. So there we go. Basically instances. That's the number. Instances. There we go. Yeah, that's the number we want to have in there. We want to have an open parenthesis. We want to have instances. We want to have a closed parenthesis. And that's going to be our new name. And basically what we want to check is if fileNames includes that new name, well, then basically we should probably increase instances, right? Instances should increase. So like move on to the next one there. And then finally, once we have like a new file name, we know it's going to work. It's not going to be a problem. And we're going to say fileNames.push that new name. There we go. Okay, so is that going to work? Let's give that a try. And no, it's not quite working. So let's see. Looks like it's sort of working. Let me just make this a little bigger for now. So, okay, first one, they match up, doc and doc. And then the next ones match up too. Doc1, image is fine, doc1, 1. Look, it seems like it's working perfectly up until we get to this point right here, where basically we've got, it should be doc2 here, we're saying doc1. So we're gonna have to figure out what's going on there. So what's going on there? Well, I think basically the idea is, I think it might have something to do with this right here. Because basically we're saying we've got instances, which is 1. We've got new name, which is going to be name plus, this number in parentheses. And then we want to say, well, if it includes that new name, then we're going to increase instances. The thing is, we're not actually changing our new name after that. So I guess we should probably do that. So we'll just copy this part over here and we'll put it in here so that it actually does modify the new name. Because keep in mind, because this is a little bit nuanced here. Basically what I did is I only increased instances with the knowledge that new name was created using the value of instances. But when we create new name, that's it. It's been assigned that name. It's going to be that string. It's not going to change when we change the value of instances afterwards. So we need to reassign it and say, oh, okay, so instances is actually bigger than we thought. Let's reassign new name now. Okay, and then we do fileNames.push, new name. And is that going to work? Let's see if that actually solves the problem. Well, it did solve this problem. So these two are working just fine now, but now the other ones aren't. So, okay, all kinds of stuff going on with this one. Is this a good one to look at? Is this a better one to look at? Let's take a look at this one. What's going on with this one here? So we're trying to push in A at 1, A at 6, and then just A a whole bunch of times here. So A at 1, A at 6, A. I think, yeah, those are fine. Those are matching up. Let's get even a little more room in here. Okay, so yeah, first 3 totally matching up. In fact, the first 4, because A at 2, no problem. A at 2, great. But now we're saying A at 3, A at 4, A at 5. What's going on with these? Why is it stopping at 2 each time? Let's investigate. Oh man, this is like a 1 pixel window to drag that thing down. Okay, actually that's probably too far. Let's split the difference a bit. Okay, great. So, all right, going back to this, let's take a look at what's going on. So as soon as it does discover that fileNames includes the current name. So let's start with, I guess it would be like the 3rd A here, like the 5th element here. So as soon as we try to put that one in, we're saying, well, does it include A? And yeah, it's already got A in there. So we say, okay, well, let's let instances be 1 and new name is going to be this thing. And then if it includes that, so basically if instances is 1, then this would be A and then a 1 in parentheses. Okay, and does it include that? Well, yeah, it's right here. So yeah, it includes it. Okay, well, in that case, let's increase instances and let's reassign this thing. So now it's going to be A. I keep wanting to say A at 2, like thinking of function notation, but I'm trying to break that habit. A and then 2 in parentheses. Okay, and then what we want to really be doing is checking, well, do you have A and then 2 in parentheses? It's really hard not to say A at 2. Anyway, the point is that in there? And we want to be checking that, but we're actually not, because this is just an if statement. This isn't like repeating. So let's make it repeating. Instead of an if, let's make it a while. Like keep this going until it doesn't include that new name anymore, because that's really what we're looking for. Something that is not included yet in file names. Let's give that a try. Ooh, and look at that. So it's passing the sample test. There we go. Okay. Okay, so it's passing the sample test. That's great. Let's try submitting it. We'll see if it passes the hidden test. Ooh. Okay, not bad. It is passing the hidden test, but is it passing the hidden test well enough? Oh, hey, thanks. That's nice of you to say, but no, not right now. Okay, so what I mean by that is I'm looking at this and I'm thinking, well, could this be better? Like, we've got some code here that seems to be working, but I do have to say, I've got a couple issues with it. So the first issue I have with it is mainly this thing right here, the includes part of it. I see the includes as a problem, or at least, okay, I don't want to say necessarily a problem, but I see it as like an inefficiency, because when we're doing includes here, basically we're just checking like, you know, is this thing in the array? And really, it's an array. So the only way we can really check that is to go through and say, okay, is this the element? No? Okay, is this the element? No? Oh, all right, is this the element? No? Okay, is this the element? It is? Okay, great. So this could take some time. This is basically going through the entire array. Or at least that's the way it would work in most languages. I'm not actually 100% sure about JavaScript, because I've heard some weird things like that. A lot of JavaScript interpreters use a hash table for arrays, and so if that's true, it actually would mean that the lookups are going to be fast. So again, you know, I'm not 100% sure about this, but that's my understanding right now. And at the very least, you know, this would be applicable to other languages, if not this one. The point is, we're trying to think about like efficiency here, right? Like time complexity, that kind of stuff. So instead of doing it this way, instead of just having this array of file names and seeing if it includes that new name, instead I'm going to use something a bit different. So here I'm going to use an object. And so for this object, so again, it's not an array, it's not like just elements with index 1, 2, 3, etc. It's a full-on JavaScript object now. And so it's just going to have keys that are whatever kind of value we want them to be. I'm basically just going to use the names as the keys here. Okay, so that's basically the idea. The names are going to be the keys. And then what about the values? So this was another issue that we were having with this one. Like the instances over here, it always started at 1. And so in the sample test, we had one, yeah, this one over here, like we're inserting a whole bunch of times. And like you'll notice this last one, the instances, I guess we're calling it here, the file index, whatever we want to call it, it's going to be going all the way up to 11. And keep in mind, like, okay, I realize the constraints are not too bad on this one, but what if they were, right? What if instead of 15, what if this could be as long as like 15,000, right? If there could be tons of elements in here. So we could potentially end up spending a lot of time starting with this instances at 1 and then incrementing. Like this is just going to keep firing. It's going to increment instances just by 1 each time. It's going to reassign the value of new name each time. It's going to do that. It's going to go from 1 all the way up to whatever number it needs to be, in this case 11, but again, what if it was 15,000? That could take some time, especially considering if it was 15,000, that would mean it would have had to have been 14,999 before that, and so this would happen a lot of times, is what I'm trying to say. So basically, instead of starting with instances as 1, we want to start it as, I guess, whatever it was before. So basically, we're going to say this. I guess I'll call it file index for a few reasons. I mean, mainly just, we could call it I'm going to call it file index right now, just because I feel like that's a little more clear in terms of what we're trying to do in here. So we're going to say let file index be assigned the value of file names at name. Okay, so you might be looking at this and thinking, okay, but what if this doesn't exist? You know, like what if this is just a null? You know, what if we can't get a file index? And great. You know, if that's the case, well, that's information. So that means this is really what we're trying to check. Did we get something out of that or did we not? So if the file index already exists, well, that means there was something that we've already stored at this key. Okay. Else, if we haven't, then this is where we're going to do something like this. Except we're not going to do it quite like that because push is for arrays, right? So we're going to say file names at name is assigned the value of 1. Why 1? Why not, you know, store the name or something like that? Well, we are storing the name. We're storing the name as the key, and that's really nice because it's freeing up the value to allow us to store the actual number, the counter, the file index in this case. So we're starting at the 1 here, which means the next time we do this, if we had the same name, file names at name, we would just get that 1, which is great because it means we don't need to worry about this instances thing anymore. So we can just say, we can simplify this a lot. So we could say, first of all, okay, so new name is going to be file index instead, and we'll replace that down there. And then let's see, I guess, it's not instances anymore, it's file index. Okay, and then we'll do that. Let's see, is there anything else we want to change here? Is this going to work the way it is? Actually, no, it's not, for a few reasons. First of all, includes. Well, what are you talking about, right? It's not includes, it's that we want to be checking, well, does it exist at new name? So basically, does this have a value? Have we given this object a key that matches new name? Has that happened yet? And basically we want to say, well, if it has happened, that's no good. We actually want to increase the file index here. And then finally, once we settle upon one that actually does work here, then we want to actually, we don't want to do push. We want to say file names at new name. And keep in mind, this is going to be a new one, right? This is going to be one that we haven't encountered yet. So we want to say it's 1. The number of times we've seen this thing? Yeah, it's 1. We haven't seen it more than 1 time. Okay, so should we run the tests on that now? Is that going to work? No, it's not working still. Mainly because we're talking about an object, you know? We're not talking about an array here. But in terms of the keys, it looks like they're working pretty good, right? Like the way we want, I think, more or less. Maybe. Anyway, let's go over here. We'll see if this one's working. Yeah, it seems like we're getting the right stuff here. But, I mean, okay, I have to say I'm kind of glad that we're seeing this now because what we're seeing, okay, first of all, okay, I'm going to modify this just slightly. We're going to use something I don't know if we've used before. It's object.keys, and it's basically something that we can use to just get the keys, like to represent the keys of the object as just an array. So let's try that, object.keys file names. Okay, so that is working. It's giving us the right stuff here. But something I'm noticing about them, or something I did notice about them before, I'm just going to get rid of, or I'll keep the object.keys there, but just on top, just so that it doesn't run. I'm going to do return file name so that we can see the actual objects here. So the reason I wanted to show this is because it seems almost like, well, what was the point of storing these 1s here if they're going to stay 1s the whole time? Like, shouldn't this thing be incremented? Shouldn't this have gone up? So basically, I think what we want to do here is we want to say file names at name, like the original one, is now going to be file index. I think that's the idea. Maybe it should be -1 or something like that, but let's see if that runs the way we want it to. So yes, yeah, that looks better, I think, so far. Let's just verify that for these other ones. Yeah, great. So that makes a lot of sense, I think. It's basically saying, like, yeah, we only have one A at 1, we only have one A at 6, But for these A things, we've got to go all the way up to 11 to accommodate these things, because these were all just A, right? So it's nicer to see the 11 here. Why do I prefer that? Well, basically it means we're not repeating this. We're not repeating this loop if we don't have to. The way it was working before, basically we were starting at 1 each time. So file index would always start at 1 and then just increment, go up by 1 each time until you find a spot that's available, until you find like a key where we haven't actually placed a file index yet. Okay, so then by doing this over here, we're basically saying, okay, now remember how far you had to increment in order to find one that would actually work for this name, right? Because that way, the next time we go through this, the next time we say, actually there is a file index at that name, the next time that happens, then we'll say, oh, well, we left off, like what was the number where we left off? Because that was like the smallest one we could accommodate back then. Now we have another one, so it's probably going to be at least 1 bigger. The reason I say at least 1 bigger is because you'll notice, like here we jump from A to A at 2. We jump from A at 5 to A at 7. Why is that? It's because we already inserted the A at 1 and A at 6 as our first elements here. So they already existed, and it wasn't because we had that many elements that were just A at that time. It was because we specifically had ones like that. So that's why once we went from we'll use this as an example, from the A at 5 to the A at 7, like it jumped up 2 instead of 1 because, yeah, it was already occupied by something else. So that's why I'm saying it'll go up by at least 1 each time. And that's why I'm not just doing like a plus on this thing. That's why I want to just store the actual file index here. Okay, so let's run the test again. Let's make sure that's working. Let's get that magic pixel and we'll just show everything on screen. So yeah, again, it's not working and it's because we want just the object keys. Let's also try to tighten this up a little bit, maybe so it doesn't take up quite so much space. Yeah, let's run the test on that. There we go. Yeah, it looks like it's passing the visible tests at the very least. A little more room. Okay, and let's try submitting it. We'll see if it passes all of it. And it does. Okay, cool. So that's better. I like that better. I think it's better than what we had before. Ooh, I can't really compare to what we had before because I forgot to wrap it in a comment. So let's try this. I'm going to try copying this. And now let's do a billion undos to get it to the point. I basically want to get it to the point where this thing is no longer an object. There. Okay, I think that's what we had before. We'll run the tests on that. And yes, okay, so that was like our working version from before, and good. Okay, that copied properly. So now let's wrap this guy up down here. I mean, I guess we don't really need to comment it out since it's not going to run after the return, but just to do the interpreter a favor so that it's not going to be like, well, hey, I thought file names was this thing. You're going to give me a let down here. I don't know if it's going to have an issue with that, but yeah, might as well just keep this the only code that it's actually going to look at. Okay, great. So I like this better. I think this is a better way of doing it. I think this is going to be more efficient in terms of the time it's going to take to look these things up, because it's not doing a dot includes anymore. It's just going right to this thing. It's just saying, oh, is there something with that key? So it's kind of like the difference between looking at like, yeah, it's the difference between searching for a value in an array, like saying, okay, give me the index that has a value of 5 or -1 if it doesn't, right? It's the difference between saying something like that versus saying something like, give me the thing at index 5, right? So, okay, just to give a visual here, because I want to make sure it's making sense and all that. What I mean is basically this. Find element, let's just call it A, okay? Just for this. There. Okay, so find element A in our array called R. All right, so, and yeah, okay, great. So if we want to do that, we would be doing something like return r.indexOf A or something like that, versus find element with index I, which is where we would be doing something like return r at I. Okay, so these don't seem all that different, but what I'm trying to say is behind the scenes when we're doing an index of, it's basically saying like let index be assigned the value of -1 for element of array. Let's not forget the let. For let element of array, if element equals a, then return, ooh, and I do need the index here, right? So that's not going to work. For let I is assigned the value of 0, I is less than array.length, I plus plus. And if element, well, basically what we mean is if array at I is the same as a, then we're going to return I. Yeah. And actually, I guess because of that, we don't need this let index thing. I was thinking we would like store it and then return it at the end, but then at the end we would just do return -1. There we go. So basically all this over here is what we're seeing over here. So now this is not really looking as efficient as something like this, because you'll notice like this right here, array at I, that's something we're doing up here anyway. So, you know, we're doing a bunch of these already, like potentially as many as there are elements in the array. So this could be really inefficient, or again, at least historically, like this would be something that's kind of inefficient. Again, I'm not exactly sure how JavaScript interpreters are going to be looking at, or JavaScript engines, how they're going to be like interpreting these arrays and stuff like that. It may very well be that this actually is more efficient than I'm giving it credit for, but basically behind the scenes, that's fundamentally how an index of is going to find the element, right? So all I'm trying to say is if we're trying to find a particular value, then that could take some time because we need to search the array. If we're just trying to find something with a particular key, then that doesn't take time because we can just jump right to that key. That's basically the idea. And that's fundamentally the difference between these two different strategies here. In the first one down here, we were basically storing our names as the values in this array. And that meant we didn't have any room to store the file index or the instances. And so we had to basically count those every single time. Whereas over here, we're storing the names as keys in the object. Just to clarify, over here, the keys would have been like 0, 1, 2, 3, etc. The thing is, we didn't really need to know the order. So over here, since we don't need to know the order so much, we can get away with using the keys that are the actual names themselves. And then what are going to be the values? Well, the values are going to be just the file index, like the actual numbers, the instances, these things that we were counting up from 1 each time. Now we don't need to count up from 1 because we can just store them right in the object there. So yeah, I like this a lot more. I think this is a much nicer way of doing it. But there's something else I want to talk about here. And if you've ever encountered this task, you know, out in the wild in like a one-on-one battle or in a tournament or something like that, if you've looked at this as a recovery or as a bug fix, then you've probably noticed that is really not the way they do it. The sort of default solution here is like a lot different than this. They make use of a hash table in order to basically, well, to solve some of the issues that we were having over here. So basically just to speed things up, yeah, to make it more efficient. So I think this is in some ways an appropriate situation to be using a hash table. In some ways it's not actually, because like, you know, again, if we look at the constraints here, I don't think there's anything here that's going to necessitate the kind of time complexity we're going to get from using a hash table. Like I think it's huge overkill in this case, just considering like the lengths of these things, considering the names are not that long, the array of these names is really not that long, and so like the hash table is something we'd probably use if this was like a lot longer. Anyway, okay, so what's a hash table? Well, technically, it's something we looked at before. I mean, when we're doing different squares over here, we kind of used this hash table method where basically we had a hash value, or at least we were sort of taking like multiple values and we're condensing them into just this one number that made it very easy for us to do stuff with. So that's fundamentally what we're going to be doing here. That's like basically what the hash table is going to be all about. But basically, in this case, it's going to have some added benefits. So number one, in the last one, we were basically just taking 4 numbers and turning them into one number, which made things a little bit easier. In this case, we're going to be taking these entire like names, like these whole words, and representing those as numbers, like just a single number. And yeah, that's going to make it easier to compare. It's going to allow us to use those as like the index of an array because it's a numerical index. And there's going to be some other stuff that we're going to see here. I mean, in a sense, it's kind of like we're encrypting the names, you know, like we're not representing them as strings anymore. We're going to be representing them just as just like a number. So basically, yeah, that's the idea. Like it would give us some added security. Let's say if we didn't want to store these as clear text for whatever reason, maybe, yeah, it's nicer to have them as like some kind of weird number. So let's start with that. We're going to do a function. And by the way, just as sort of a disclaimer before we get started, I am going to model this solution, or at least the first solution we look at here. I'm going to model it after sort of like the official codefights solution of this, so the one that we would have seen in that code battle video from way back. It's on my YouTube channel if you want to take a look. But basically, we'll do this calculate hash function, and it's going to take as an input a string, because that's what we're dealing with here, right? Okay, and we want a few values here. So first of all, this limit value, we're going to make it sort of a large prime. So I'm going to go with 32,099. Maybe there are better values to use. I mean, it's almost a guarantee that, yeah, there are better values to use here. I mean, the thing is, my understanding of this, what I've heard anyway, is that creating a hash function, like what I'm doing right now, this calculate hash thing, is kind of an art. It's the sort of thing that's not so much a science, but more of an art that, you know, you sort of have to tweak it, you sort of have to work with it. My understanding from what I've heard is basically that people tend to use functions that have been already sort of like created by people who know what they're doing more. Anyway, for this one, I don't think it's going to make a huge difference. I'm just going to use our own thing here. It's just going to be very simple. So keep in mind, like what we're doing here is, it's going to be pretty rudimentary. So, okay, I basically want to take the hash value, doing some math stuff in here. I think I have one too many sets of parentheses there. I'm going to take that hash value, I'm going to multiply it by another prime number, so I'll use 257. And we're going to add the character code of our current character in the string. We're basically taking this string, we're going through the string one character at a time. We're saying, let's add that character code, and whatever the hash value was, we're going to multiply it by some prime number. And I specifically used a prime number that's probably going to be bigger than any of these character codes. I mean, I don't think we're going to be spelling these file names with any of the extended ASCII codes or anything like that. So probably even something like 127 would be big enough. But just to be sure, I guess we'll use this value over here. And again, I mean, there may be some other considerations here I'm not familiar with, but that's my understanding anyway. And then we're going to mod that with the limit here. Finally, we're going to return our hash value. So this is basically like a function that's going to take a string, it's going to convert it into some number, and from what I understand anyway, we want these numbers to be like pretty well distributed. We want them to spread out pretty nicely, and that's why we use like a large prime number as the limit. Like if you think about it, if we were to use a number like 10,000, that's very not prime. It has a lot of factors, and so because of that, it would not be relatively prime with a lot of other numbers. So like if we had some multiple of 5, like if we were increasing something by 5 each time, and then we were doing mod 10,000, well, it would repeat on the same, like it would hit the same numbers each time. Let's get a visual in here. So basically, we need a nice color to start with. Okay, cool. So, all right. let's say, you know, we had this kind of like number line, right? And the length of it we're saying is going to be like 10,000 or something like that. And then basically the idea is we're going to have elements. If we were increasing by 5 each time, or like 50 or something like that, then we'd say, okay, start here, increase by this amount, increase by this amount, increase by this amount, increase by this amount. We're increasing by the same amount each time. And then basically if we were to get to the end and it was like a perfect fit here, then when we do mod, you know, 10,000 or whatever it is, we would just start right back at the beginning and we'd be right back at this number and we'd increase and hit that number and hit that number and hit that. What I'm trying to say is most of the numbers here we would never ever encounter. Whereas if we were to change this and say, you know, if it was like a relatively prime number, so like if this number that we're increasing by didn't have any common factors with the number that we're modding, like the length of this thing, then basically we'd have something more like this. We increase, 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 and then we get to the end here and we try to increase and we say, oh, well, you know, we're cutting it off there. So then we would land at like a different space the next time when it wraps around. And so then we would hit a whole different set of numbers on the second go around. Okay, that's getting a little messy, but the point is, we're using prime numbers here just so that we get less repetition, so that like if this was to sort of loop around, it would loop around visiting different numbers this time. So why do we want to be visiting different numbers, I guess is a good question, a question that's worth asking. So yeah, let's try to answer that question. Should we try to answer that question now? Yeah, I guess so. So basically, actually, hold on. Before, I don't want to get ahead of ourselves. We've got this calculate hash function. We've just written it out, but does it work? Let's try it. So we'll say return calculate hash, and we'll put in a string. Hey, what's up? Let's see if that works. Okay, yeah, it's giving us a number. What's the significance of that number? Hard to say, but it's giving us a number anyway. All right, so is that good? Well, I don't know. I think not, actually. I think there's a problem with this because I'm noticing that that number is very, very large. In fact, it's larger than our limit here. I think what I meant to do is this, not plus equals, because basically it's taking the current value already, it's multiplying it by this fairly large prime number, and then it's adding this character code and saying, oh, okay, well, hey, if you've gone too far, if you've gone above this value here, let's mod that. So let's run that now, and we should get something that's, I guess, below 32,000. Great, okay, that's looking better. Okay, so calculate hash of, hey, what's up? It's 21,595. Let's do something else. It's a very nice day. And we'll see if we get a different value from that. Yeah, we do. Okay, so that's good. We should get different values for these. But the thing is, there's going to be a limit to that, right? Like, we're only going to have 32,099 possibilities here. And conceivably, there are going to be more than 32,099 possible combinations of strings or characters that we come up with to make these different strings. So yeah, that we might run out of room here. We might have collisions in our hash table. But I don't want to get too much ahead of ourselves. Let's actually talk about what this hash table business is all about. So another constant here. So this one is going to be the hash table length. And we're going to make it 2 times the length of our initial array names. And that's just to sort of give some breathing room here. We'll talk about why we want that kind of breathing room in a minute when we talk about this linear probing strategy we're going to use. But first, we'll say let hash table be assigned the value of an empty array, and let file names also be this empty array. So the file names is where we're going to store our results. The hash table is where we're going to keep track of what we've already encountered here. Okay, great. So what do we want in our hash table? Well, again, I'm sort of modeling this after the solution, the official codefights.com solution here. So I'm going to go all the way to hash table length here, and I'm just going to keep this iterator going. And basically, each value inside our hash table is going to be something like this. So it's going to be a little array. what's that array going to have in it? Well, it's not going to have much to begin with. It's going to have -1, it's going to have null, and it's going to have 0. Okay, so that probably doesn't seem all that exciting here. Basically, the idea is I'm storing 3 things. So this is going to be, in fact, let's put it in a comment. So basically inside here, we have the hash value. That's the first thing. So like the thing that we're going to get from our calculate hash. We're going to have the name itself. So like the thing that we get from the names array. And then we're going to have the number of instances, or like the counter, or like the file index, you know, whatever we want to call it. But like the thing that we've been using downstairs here to sort of like count this up, the thing we're going to be putting in the parentheses. That's basically the idea. We're going to be pushing in this array, which is going to start, we're going to start with a hash value. Well, there's no hash value, so we're just going to make it -1. Then we're going to say, what's the name? Well, we don't have a name yet, so that's just going to be null. And how many instances of it? Well, 0. It's not a thing yet. So that's what we're going to start with. And then basically the plan is that for each of our names, we're going to calculate the hash value. And then we're going to put that in here. We're going to put that at the correct index. And then after that, we're going to put in the name. We're going to put in the instances. And all that kind of stuff. So before we do that, though, we should probably take a minute to maybe sort of zoom out and think about what these hash tables are all about. Why we want to use them, what they're going to do for us, that kind of stuff. So let's take a visual look at this, I guess. So I don't know if I cleared the whiteboard from last time. No, I didn't. Okay, let's do that now. Where's the button for that now? They rearranged all this stuff with the update, but it is a very good update, so I'm not mad about it. Okay, so here we go. And we're going to draw, using a much finer pen, we're going to draw an array. And our array is basically going to look like this. And I know there's a straight line tool now, but for old time's sake, we're going to go with wavy lines. Okay, cool. So we're going to have like our, oh, that's too far. We're going to have some array values in here. And basically the idea is that for each of these things, we're going to be storing like all that stuff that we were looking at just a second ago. But the main thing is that basically we take a name and we want to say, like, whatever the name is, I don't know what they have here, doc. Okay, so we'll take doc and we'll encode that as some kind of number. And that number we're going to use as the basis of the index in our array here. So we'll take that number and we'll mod that with the length of the hash table, and then we'll say, okay, so you ended up, actually let me switch colors for a sec here. We'll say you ended up right here. Okay, that's where you ended up in the hash table. So that's where we're gonna save your data. That's where we're gonna put this array with, like, it'll have the hash value itself, it'll have the string itself, like the actual name, and it'll have the number of instances. All of that information is going to go right here. So then the thing is, well, what if we need that again? We don't want to have to like search the whole array and like check for that thing. We don't want to have to do like that include stuff that we were doing before, like an index of. We don't want to have to go through every element in order to track down the one we're looking for. The thing is, the way we were able to find this value initially is using our hash value, by calculating our hash value, and that was just from the name. So we can always convert the name into that hash value, which makes it essentially synonymous with the index here. Well, that's great. And then, later we would have like another element, and let's say it ends up getting stored over here, and that's great, and we'll get a bunch of these things in here, and basically we'll just, every time we get the same hash value, like every time we have, let me rephrase that. Every time we end up with the same string, so like here we have doc, here we have doc again. So we have the same string, that means we're gonna have the same hash value. So they're both gonna lead to the same thing. So again, let's say like this is where doc ends up. And this one is where, I don't know, maybe image ends up. Ooh, bit of jumpy mouse action here. Image. Okay, cool. So basically the idea is that doc is going to be over here, image is going to be over here, so that when we do doc the next time, well, it's the same string, right? The second time it's the same string. It'll have the same hash value. So it'll therefore produce the same index in the array. So we'll say, oh, okay, well, is there something there already? Oh, there is. Okay, so there must already be a doc there. So we'll increment the number. So, we're going to change like some of these values in here, basically. But the idea is that every time we have the same string occurring, it will point to the same index of the array. But is that the only time we're going to have two things pointing to the same index of the array? And I'm just going to use that as a bit of foreshadowing here for now. We'll talk about how we're going to deal with that in just a minute. Okay, so for now, we're going to do something like this. Let's make a function that's basically going to be used for finding that index. We were saying that over here, if we want the word doc, let's just arbitrarily say it's going to be this index over here. And again, like if the hash value is too big, we're going to mod it with the length of this thing. So it's kind of like, it's going to loop around kind of thing. Anyway, point is, that's what we want to find. We want to translate it into an actual index that's going to fit in this array. So we're going to say find index. And what information do we need to find this index? Well, I guess the main thing that we're going to need is the hash value. So let's put that in, hash value. And basically, essentially it's going to be this, right? Our index is just going to be the hash value, whatever it is, whatever hash value we're getting from that, modded with our hash table length, because that's the maximum length we can get. So let's try that for now. We're just going to do that as our find index. It's going to take us to the place where that string is going to be located. And then what are we going to do from there? Well, it seems like we've got all the machinery set up now. I think we're ready to actually start going through the array, start taking a look at like what names we have here, and then do stuff with those. So let's get that started. So we're going to say for let name of names. Again, we don't need to know what index they were in the original array, and we're going to be going through it in order, but we don't need to know specifically which index it is. What we need to know is what the name is, because we're going to use that in order to generate the index for our hash table over here. Okay, cool. So let name of names. What are we going to do with this? Well, very first thing, we're going to say hash is going to be assigned the value of calculate hash of name. We're going to take that string, we're going to get a hash value using this function right here. So we're going to convert that string into a number. Okay, great. And then we're going to say let index be assigned the value of find index with our hash value. Yeah, we're just going to find that index. So that's just this function we were doing over here. Maybe even seems like overkill to use a whole function for that. Like I could just put that in line over here, just index is assigned the value of hash table mod hash table length, or sorry, hash value mod hash table length. But might as well keep it a function. Maybe there's a reason for that. We'll find out later. The point is, let's continue for now. So basically, we want to do a similar kind of check as what we had down here, right? Down here, we're basically saying, well, does file names include name? Like, do we already have this name? But now instead, we're using the hash table to make those kinds of calls. So we're going to say if hash table at index. Now keep in mind, hash table at index is going to be something like this. In fact, okay, before we go any further, I'll say do something, there we go. Before we go any further, I want to take a look at what the hash table actually looks like, because we haven't actually seen it before. So let's return hash table and get a bit of space here. So yeah, that's what it looks like, just -1, null, 0, -1, null, 0, -1, null, 0. That's how it starts. And so once we get to this point down here, we've got hash table at index. Okay, it's not going to be as simple as that, because hash table at index is just going to be one of these things. What we want to know is it one that's had some information stored in it yet? Have we actually put a name into there yet? And the way we're going to tell that is, well, what's the instances? How many instances of whatever thing you've got here have we encountered? In this case, it's 0. We don't have any instances. So that's what we want to check. We want to check if the thing at index 2 within this array here, like smaller array, if that's going to be 0 or not. So we'll say this thing right here, is that 0? And if it is, then we'll say, okay, great, you know, that works. Like, we haven't seen this word before. This is a new word. And so we'll say, okay, well, let's just take that hash table at index thing right there. And we'll basically say now it's going to have our hash value. It's going to have the name. And it's going to have an instance of 1 because we found one of them. And since we have found one of them, and like this was fine, we inserted it there, and no one was upset or anything like that, we'll do fileNames.push name. That worked, you know, we were able to just put that name right in there. So we'll just push that to our file names array, which again is the thing that we're ultimately going to be returning at the end here. Okay. And we don't want to put that return. I might as well take that out before I forget it, because that is the sort of thing that would really mess with this if I had forgotten to take it out. Okay, cool. So then, actually, you know what? I'm just curious, like, what is our hash table going to be looking like now after we execute this? And what we can see is a couple of these things are going in and a couple of them are not going in. Let's try to figure out what's going on with that. So basically, we're saying for doc, we were able to find that thing, right? And, well, hey, that's funny, because I put it at like index 2 over here and it happened to be at index 2. That's freaky. Did I get the other one right? No, that one's way off. Okay, so basically the idea here is that we've got the hash value, we've got the name itself, we've got the number of instances of it, but we're not actually dealing with the situation where that's not the case. You know, if we don't find a 0 here, like if we find a 1 or something like that. So keep in mind, we've got doc, we've got these other names that are basically the same as this one. So right now it's just looking at us and saying, oh, there's already 1 there, so I guess we're not going to do anything. But we actually want to do something in that case. So let's put the else in here now. And basically what the else is going to do is sort of like what we had down here when we were getting this new name stuff, like where we had said, oh, okay, well, we already found that name, like that one's already in there, so let's modify the name. Let's put that thing in parentheses and then we'll keep that going until we can actually use that new name. So, okay, we'll go to here and we'll say, all right, well, let's let that new name be whatever the name was. Plus, we know that in this case, hash table at index at 2 was not 0. It was something other than 0. So basically, since we know it was something other than 0, we can use that piece of information. So we can actually say, okay, well, let's spell this correctly first of all. Let's take hash table at index at 2, because that was something that's not 0. So let's actually put that in here, that we can use that number. And then we'll close off the parentheses and we'll see that's our new name. Okay, once we've done that, then basically we want to say, well, we've got a new name. We might as well get a new hash value. So we'll do calculate hash with our new name. And so now basically, since the name has changed, the hash value will change as well, which means the index will change also, and we'll end up just at a different spot in our hash table. Okay, cool. So where are we going to end up in the hash table? Let's find out. So we're going to do new index, and it's going to be find index of our new hash. Okay, cool. So we've got some new information here. This is good. And then basically we want to do, again, the same thing we did down here. So we're basically saying, okay, well, now we've got a new name. And until we find that that new name has also been recorded, we want to keep pushing this like instances. We want to keep increasing that thing. And then finally, we'll once we find one that is like we haven't encountered yet, it's a new file name, it's valid, it's good, it's unique, then we'll push that into file names and everyone's going to be very happy. Okay, so let's do that. So we basically want to do a while loop, and the while loop, okay, we got to pay very careful attention to this one because it's maybe going to look a little bit confusing at first. It might look like like we're repeating ourselves, but we're doing something slightly different here. So keep in mind, we're now looking at hash table at new index. So keep in mind, it's not the same as hash table at index. Hash table at index still, like we're still looking at that. We're still saying, oh, okay, well there's doc. We're trying to insert a new doc. Well, we can't put it here. Where can we put it? So can we call it doc1? Is there already something called doc1? I don't know. We have to look at, whatever part of the table here would actually store that doc1 value. So let's try that. So, while hash table at new index at 2 is not 0. So like until we find one where, yeah, there are no instances of that, then basically we'll keep this moving, we'll keep moving it along. So we'll say, okay, well in that case, so hash table at index at 2 plus plus. Okay, now that is a really, really important line to pay attention to. There's something going on there that's a little bit different. Okay, actually, hold on a sec. Take a minute to digest that. I'm gonna be back in just 1 second. Okay, sorry about that. So, in case you didn't figure it out, basically this part, since that's still index, not new index, but just index, that's basically taking a look at this value right here. And it's saying, okay, well, we tried to put doc at 1, or like doc parenthesis 1, close parenthesis. We tried to put that inside the hash table. We found there was actually already something there. It looks like we already found a doc1 before, so that means we can't use doc1. Should we try doc2? I guess we should, so let's try increasing this to 2. So that's why we're saying hash table at index, not at new index, but at index, the one we started with, at 2 being, 0, 1, 2, so the numerical part of it, plus that thing. Add 1 onto it, make it bigger, and then we'll basically try it again. So we're gonna take all of this stuff, it's gonna be almost no different. We're just gonna paste that in here. We'll tab these guys over. But now we need to get rid of these lets because we're not like, declaring a new variable. Like we already know what new name is. We already know what new has. We don't need to put in the let. In fact, it would be a problem if we did because it would limit these ones to the scope of this while loop, and that's really not what we want. Okay, so basically, we're gonna keep calculating these things until we find, oh, you know what? We actually don't have that one yet. And then we'll say, oh, okay, it's fine then. And this will have been incremented to the right value, meaning that the next time this happens, we won't have to start at 1 like we did initially with our instances. We can just start at whatever value was stored in there. So that was the advantage that was afforded to us by this other strategy we're using with the object, but we can use that again with our hash table here. And maybe there's gonna be some other advantages to the hash table as well. We'll find out. But anyway, for now, we're almost done. We basically just have one thing left to do. And it's that we want to, well, actually sort of 2 things, I guess. We want to modify the hash table. So we'll say, well, we found the index now. So hash table at new index is going to be new hash, new name, and 1, because this is the first one that we found. And then after that, we want to say, well, yeah, we found the file name, so let's push the file name, which is going to be new name. Okay, cool. Well, that's great. Very nice. Okay, so is that good? Is that working? Is it working? Let's find out. So, all right, we've got some stuff in here. Looks like we've got doc being stored at 1 address. We've got, and notice the doc has been incremented to a 2 here. It's not like a 1 like all the others here. We've got a doc1, which has been stored, and there's only one of those. We got a doc2, and one of those as well. We had a doc11, which is kind of weird, but can happen, and we have image1. Now I have to say that image1, that one's a little strange to me. So I'm a little surprised by that. Why did we get image1? Because like there was no image before, like. And in fact, like, okay, let's do this, and what we should find is that first one, not quite working. Now, one of them did work. This one, not a problem. But this one over here, didn't work so good. So, why is that? Could it be I'm just curious here. Could it be, let's get the hash table back in here. We'll run this. I'm wondering, the index that we get, so let's try this, okay? So right before the return here, let's do a console.log. What are we gonna log here? Basically, we'll do find index of calculate hash of the word image. And then we also want to do the same thing for doc1, was it? I think it was doc1 that was giving us that problem. I'm just wondering if we're actually getting the same address for these things. Yes, we are. We're getting the same index. So we have ourselves a collision. Oh, and look at this. Yeah, this actually is 3 from the bottom. Wow. Very prescient. Okay, so this is what happened. Basically, okay, this is, it's kind of more the reverse of what happened. Let's erase this. We'll say, no, it's not image here. This is where doc1 ended up, right? That's what was happening. So, okay, doc1. And I'm only now noticing that the pen size is independent of the eraser size. I gotta say, AWW app, like, you guys are killing it. Okay, so this ended up being stored here. And then basically, this other one, image, ended up getting the same index. And that's a problem. That's really no good. We don't want to have this kind of thing. So this, as far as I understand, this is what's known as a collision. And there are various ways of handling collisions. But there's something that we don't want to see, because it means basically like we've got two different names here, and I mean they should be like different hash values as well, but yet they're getting mapped to the same index of our array. Now, I think part of the issue here is basically, my hash function here probably wasn't good enough. By doing a different hash function, I think we probably could make it better. I don't know. I mean, maybe if I'm curious actually, if I was to just get rid of this here, I think it was just one of them that was working, right? Like the other two were having some problems. Yeah. I'm wondering if I was to like modify this, would that have enough of an effect on it to actually change the results? Well, yeah, apparently it does. Not for the better though. I'd suspect if I messed around with the numbers for long enough, we could probably find one that works, but, should we rely on that? Like, aren't there eventually probably going to be some collisions? We want to be ready for the possibility that, yeah, maybe there are going to be some collisions. So this actually brings us to an interesting point. So let's just delete some of that stuff. I'm going to minimize this a little bit. We're going to go up here and we're going to modify this. So this is maybe pointing to the reason why I wanted to use this find index function. Again, it probably seems kind of strange to use a function for something so simple. Well, it's not going to be quite that simple anymore, because basically what we want to do now is we want to say, okay, so image belongs here according to our find index function, according to our calculate hash and all that. Image belongs here. There's something there already. Now, the way we were looking at it before is we were saying, well, if there's something here already, it must be image. So instead, let's try image at 1 and put it somewhere else. We don't want to have to do that, because we should verify first. We should say, okay, so yeah, image belongs here, but is this really image? Is this the right thing? And if not, then we're going to say, oh, okay, well image belongs here, but someone else took image's spot. So we'll say, all right, instead of image going over there, let's reroute it and say, okay, we're going to put image at the next spot if it's unoccupied. Now let's say, and okay, there we go. It's unoccupied. Everyone's very happy. Now let's say we had like maybe a third element or a fourth element, I guess, and it's also something that would have the same hash value here. So I don't know, something else. Here, let's just say something Yeah, something. Okay, great. And naturally, it wants to point to this one, but that one's full. So we say, okay, well, let's point to that one instead. Oh, that one's full. Okay, let's, and just for the sake of this example, let's assume that that one's full as well, and that one's full also. Yeah. Okay, so then from there we say, all right, so something can't be this one, it can't be this one. We're going to loop around and we're going to say, all right, well, could it be this one over here? And then we'd say, okay, yeah, okay, you found it. That one's fine. You can store it there, do whatever you need to do. And that's kind of not bad. One thing I want to point out, because, you know, you might be looking at this and thinking like, well, what if it never finds a spot? You know, like what if it says, can I go here? No. 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 Oh, okay. I guess I'll go over here. Can I go here? No. Can I go here? No. Like if you're wondering, like, is this going to repeat forever? Is this just going to keep looping again and again and again? The answer is no, it's not. That's a guarantee. And the reason we know that is because we only have like however many names we have. If we have 5 names over here, then because of the way we constructed our hash table length over here, it's 2 times the length of this thing. So not only will we never reach a situation where these are all going to be full, we're never even going to reach a situation where where this table is more than half full. So we probably are, like, this probably isn't going to be too bad, but also at the same time, we don't really want this kind of thing happening. You know, we call this clustering, I guess, where we get a bunch of values that are like around the same area in the table. We don't really like that because it means like basically every time we call something, like keep in mind, something is supposed to be over here. Like this is the proper location for something. And then we say, oh yeah, well, that one was taken and the one after was taken and the one after was taken and the one after that was taken. So I ended up over here. Well, okay, that's fine because we found a spot for it, but that means every time we look this up, because keep in mind, the point of this is quick lookups, you know, so that instead of having to say, like, having to go through an array and say, hey, is this one image? No. Is this one image? No. Is this one image? Oh, okay, there it is. Instead of having to do that, we want to be able to just say, I want to find the location where image is. Where's image? Here it is. Great. But instead, if we do that for something, then we'll say, okay, I want to find the location of something. Oh, it should have been here. But it's not there. So, okay, I guess we'll find, is it the next one? No. Is it the next one? No. Is it the next one? No. Oh, there it is. That means every time we look it up, it's going to take that extra bit of time sort of cycling through these. Not ideal. You know, we'd prefer to avoid that if we can. So, I guess, yeah, let's try to avoid that. But, okay. This all goes back to, like, you know, building a good hash function and all that, like the calculate hash function. If we make it a better function, it'll spread these out more. It'll reduce the possibility of collisions and clustering and all that kind of stuff. But I think there's only so much we can do in some situations because, again, like, there's so many possibilities. If we have like 128 options for each character, and even for something like this with just 15 characters, I mean 128 to the power of 15, well, I'm not very good with numbers, but I think that's going to be pretty damn big, like probably bigger than the 32,099 that we have over here. So because of that, I sort of feel, and, you know, correct me if I'm wrong if someone knows better than me, but like I sort of get the sense that collisions are something that you maybe sometimes can't avoid. So because of that, we're going to try our best to avoid these collisions, or at least we're going to try to deal with these collisions when they do happen. We'll try our best to avoid them, and if they do happen, we'll try to deal with them gracefully. So let's do some linear probing. Okay, so linear probing is basically what we were talking about before. So basically, if the correct index is taken, go to the next one. Loop or wrap around the table if you have to. Okay, cool. And then, yeah, it's not going to be as simple as this. We're not just going to be returning this thing. Instead, what we're going to say is let index be assigned the value of that thing. You know, we're going to start with that as our index. And then basically what we want to do is we want to say, well, while it's not the correct thing, while it's not going to be indentation. Okay, while it's not going to, come on. Okay, while it's not going to be the right thing, we're basically just going to increase the index. So we're going to say index is going to be index plus 1. And that probably seems weird, like why not just do index plus plus? Well, there's a reason for it. It's because I want to mod that with the hash table length so that it doesn't go off the rails, you know, so it doesn't like go try to get this spot over here. I want it to instead loop around. So that's why we do this mod thing over here. And then finally, once it's found the right one, we want to return that index. So sorry about the weird indentation here. It's just because I haven't filled this in yet. And hey, what's going on? Come on, man, you know index. Don't be green, be blue. Okay, well, maybe once I fix this, it'll be happier with that. So basically the idea is, what we want to say here is, okay, first of all, if you encounter one where this thing, where the 0th element is -1, well, that means there's nothing there. So let's keep going while that thing is not -1, okay? Just keep in mind, they all start out as -1. So if we find one and it's -1, then we'll say, oh, we're good. Yeah, that's fine. We're done. Or also there's another possibility. Maybe we find one and it's not -1. Maybe we find one and it's got some stuff there, like it's got some hash value. So it'd be like a pretty big number potentially. Maybe it has that, but maybe it's because it is the right one, you know, like maybe it's that we were trying to look up a doc and we look here and we say, oh, well, there's something there already. It's been taken. And it's like, yeah, but it's the right thing. It's doc. So we want to check that as well. So really we want to keep this going. We want to increment our index for as long as either the thing is not empty, for as long as it's either not empty, or if it is not empty, it could be that it's because it has the right value, like the thing we're looking for. So hash table at index at 1, because this should be the name here, right, is not the same as, I'm going to say str right now, str for string, and that means we're going to have to put that in as well. We're going to have a second argument for our find index function, just to make sure it's the right string, right? Because as it turns out, maybe the hash value is not enough because some different hash values are going to map to the same index. We don't want that happening, so we want to check the string as well. Okay, so now we need to look at all of our instances of find index. It's not going to be enough to just say the hash. We need to give it the name as well. That's the string we want to be using here. Okay, and where else do we use this? Okay, over here. So name. There we go. Okay, cool. So is that good? Is that going to be enough? Let's find out. So we'll run the test here. Let's try to see the tests as well. Oh, this is a suspenseful moment. Okay, what are we getting? Not something correct. All right, that's interesting. I had high hopes for this one, but let's find out what's going on with it. So we'll return the hash table, and what are we finding here? So, okay, we have doc over here. That's still a 1, so that's sort of weird. Ooh, okay. What's going on with this? So we had doc at 1, and then another doc at 1. So that's maybe some funny business. I think it's probably because we forgot to update this one here, and this one doesn't have the name. So basically, what we were doing is basically calling find index with new hash as the hash value, but then just null as the string here. So it was basically incrementing and saying, okay, so if it's not empty and it's not null. So that's not the right thing. It should be trying to actually match it to the string that it is. So did that fix it? Doesn't look like it. Okay, so why is that? Oh, name. New name. Yeah, new name. That's really what we're trying to check, right? If it's new name. So did that fix it? No, it didn't. And it's because this one also should be new name. All right. A lot of little patches to make there, but I think that's fixing because now we see that doc has incremented to 2, and I think if we were to return our file names inside of the hash table, there it goes. Okay, so let's just clear that out of the way for now. Let's take a step. There we go. Let's take a step back and sort of appreciate what we've done so far here. So just to sort of wrap this all up, we started with this thing that calculates the hash value. That's basically taking our string and converting it into a single number, and it happens to be a pretty large, kind of weird number. We just want to spread these things out pretty nicely. And then after that, we're constructing a hash table. It's going to be twice as long as this names thing, just to avoid clustering in case of collisions, this kind of stuff like we were talking about before. And then file names is the thing that we're actually going to output. We have this thing over here, which is basically just loading up the hash table with things of this form. And then after that, we have our findIndex function, which is basically just the thing that's actually putting these in the right place. The thing that's going to say, oh, didn't work over there. Well, let's keep that incrementing until, oh yeah, okay, got it. That looks good. Okay, so that's our findIndex function. And then finally, after that, this stuff, I know it looks a little more complicated than what we had downstairs, but I would argue it's actually not that much more complicated. It's pretty much the same sort of thing. It's just doing this stuff with the hash table. So fundamentally, it's the same sort of thing. We basically find where it should be in the hash table, and then we say, okay, well, and actually, okay, when I say where it should be, I mean, like, basically the index we are going to use, right? Because it says find index, and find index is the thing that actually finds the right place for it. So we find that, and we basically just say, have we seen this thing before? And if not, we're just going to put it in. We're just going to say, okay, well, we haven't seen this thing before, so it's a new instance. There's only been one of these things, and it's a file name that we've encountered, so we're going to push that. Otherwise, if we have seen it before, so if this thing is not 0, then we'll say, oh, okay, so we've already got one of these, which means we're not going to use that one. We're going to make a new name, and basically it's just going to be that name plus in parentheses whatever, like however many times we've seen that name already, and that's why we're going to also increment that, right? Like this thing over here, we're going to say, oh, okay, so like we've seen this thing already. Let's keep that incrementing. All right. Cool. And then we get a new hash value for that. We get a new index for that, and we basically do the same thing as we did up here. We want to say, well, while that's not while that's no good, so until you find one where that's actually going to fit in, we're going to have to keep incrementing this thing. We're going to have to say, oh, well, doc1 wasn't good enough. We're going to have to do doc2. Or, in the other example, like the second test, it's like it went up all the way to A11, right? So it's like, whoa, we've seen a lot of these things. We got to go all the way to 11 now. Now, okay, after that, we basically put that new thing into the hash table and push it as a new file name. So I actually do want to see the hash table. I want to know how it turned out in the end. I'm curious about it. Basically, what I want to check is how clustered was it? Did we have a lot of clustering happening? So, we got these two kind of close together, these two close together. I think, yeah, this was the one we saw before where these two were actually assigned to the same thing. So what about over here? Well, that's pretty not bad. I think these are distributed pretty well. What about this third one? Okay, so that one might be a little worse because we sort of start off with like 4 empty ones, 4 full ones. I'm sort of curious about how many of these were actually supposed to be in the exact same spot and ended up just getting, probed onto the next one. So, yeah, clustering is, I think, a bit more of an issue in this one than in the other ones. Anyway, we were able to deal with it, and this passes all the visible tests, right? Or it should now pass all the visible tests. Great. And look at how fast that was. That was nice and fast, real efficient. Let's try submitting it. We'll see if it passes the hidden test as well. Yeah, it does. Okay, so that's pretty good. I think, again, like when I first saw this, like I was saying, this is kind of based on the official codefights solution. When I first saw it, I thought, you gotta be kidding me. That seems so much more complicated than it needs to be. What is this? Almost like, it's like 60 lines almost, right? Couldn't we get it done with just like the very few that we started with down here? Like this was getting the job done, and it was getting the job done good enough for these kinds of constraints that we had here. So basically, well, actually, if you want to go back and see it, at the time when I first saw this, I was so perplexed by it that I made a forum post. Like I went onto the forums and I was like, why are they using a hash table here? I don't get it. Doesn't this seem like overkill? And basically someone kindly explained to me, yeah, I mean, in this case with these constraints, sure. one of my old university professors used to say it's like killing a fly with an atom bomb. Anyway, the point is, it's kind of a morbid analogy. The point is, what we're trying to say is we don't need the full power of a hash table for something that's only going to be 15 elements long. But if it was much longer than that, if it was 15,000, I think this is exactly the way we would want to go. Again, though, I don't exactly have the inside scoop on exactly how JavaScript is interpreting all this stuff, so it may very well be that it's actually handling these kinds of considerations by itself, and that in this language we don't need to worry about it. I don't have the answers for that one, unfortunately. Hey, if someone knows, let me know. I'd love to hear about it. So, yeah, that's basically what we're going to do with our hash table with linear probing anyway. Again, that does lead us to this kind of it leaves us susceptible to this clustering business. I mean, linear probing basically means, well, think about it this way. If it was clustered like really badly, like if all of them were just right in the same spot, like let's say, what color have I not used yet? This one. So let's say we had one there. Now basically they're all clustered just in one big glob. And so that's kind of bad because it means every one of these that we want to look up, like, okay, and let's say that these are clustered here because they were all supposed to go to this one index. Let's say we use a really bad hash function, calculate hash function, or maybe just we happened to receive inputs that just were very incompatible with that hash function. So then let's say they were all meant to be mapped like right here. So in that case, basically every single one of these things, when we want to find the index, we're going to say, oh, okay, start here. Oh, no, can't be that one. 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 Oh, yeah, it could be that one. You know, something like that. Like it would just kind of defeat the purpose of the efficiency of lookups that we get here, because essentially it would become big O of n. And that's exactly what we were trying to avoid by having this hash table. We don't want it to be like an array where we have to do like a dot includes every time and look through it and all that. So maybe there's another way. And yeah, there's another way. So basically, another way we can handle this, and I'm actually not sure what they call this method of resolving the issue, but instead of using linear probing, instead of just like bumping it over to the next one, there we go. Nice fresh array, just like what we started with. So instead of doing it this way, like we would say, okay, I don't want to represent this. Basically, for here, we could say something like, all right, if this is where doc should be, we'll take this element and we'll say, all right, so we're going to have a node here, and it's going to have both a value and a next. It's going to have a name, which is going to be doc, and it's going to have a next. Actually, okay, it's implied that this is next. I'm not going to write out the whole thing. The next is going to be null for now. So it's not going to have a next. It's not going to be pointing to anything. And then let's say we want to get another thing in here. We'll put this over here, and this is going to be image. Okay. Image. Great. And that'll have a next as well. And then basically the idea is that when we want to insert, what was it, doc at 1? I think that's where we found our first collision. So doc at 1, actually, let me switch to a darker color. Okay. So doc at 1, we want to put it here, and we say, oh, well, that's not empty. There's a thing here. So instead of putting it like on the next thing, we're going to say, all right, well, let's go to the end. Well, okay, first of all, we've got essentially like some linked node over here. So we're going to say, all right, well, is this thing the thing we're looking for? Oh, it's not? Oh, okay. What about the next thing here? Oh, there is no next thing? Well, in that case, I guess let's just put this as our next thing. So we're going to take this, and now this is going to be doc 1. Great. And then if we encounter another thing here, or if we wanted to look up, let's say we wanted to look up doc 1 again. So we need to find it for whatever reason. Maybe like, for example, we're trying to insert something called doc, and we want to check, well, is there a doc 1 already? Well, we say, okay, so it belongs here, but here we've got this linked list thing. So is this it? Is this doc 1? No, it's not. Oh, okay. Well, let's do next. Is this doc 1? Oh, yeah, it is. Okay, cool. And then basically the idea is if we don't find it, we would just put it on to the end. That's sort of the idea. So we're getting into this new data structure that we haven't really talked about yet. This is a really data structure heavy problem, which is nice. I mean, this is, again, if you go into like the interview practice on codefights.com, like you're going to see a lot of this data structures, algorithms, that kind of stuff. We've been focusing mainly on algorithms up to this point, but now we're getting more into the data structures, and you know, it's a lot of fun, I have to say. Okay, so the idea here is that we want to use a linked list as sort of an additional data structure within the hash table. So instead of just storing the values here, the hash table is going to store these linked lists of values. So wherever we need to go, we're going to have like an element, which is going to have a next, and that's going to point to the next thing in the list, and that'll have a next, which points to the next thing after that. So we're going to be sort of like traversing this linked list business. That's sort of the idea. You know, you're going to first one, the second one, the third one, all that kind of stuff. Anyway, before we get into this, you know, before we make the modifications here, we should probably talk about linked lists, I think. So actually, you know, while we're at it, let's take a look at our Big O complexity chart. So we've looked at this before. This is bigocheatsheet.com. Very, very useful resource, nice and condensed. And I mean, you remember Big O, right? We've talked about it before. This is sort of like, in terms of either time complexity or space complexity, it's telling us essentially how, let's say we're looking at time complexity, this is giving us sort of like a graph of how the amount of time, the computation time, how it scales up with the size of the arguments. So like if we were to give it, well, this is kind of what I was alluding to over here. I was saying I sort of kept bringing back the fact that our array is not going to be bigger than 15 elements. Well, let's say it was, you know, let's say it could be 200,000 elements long. Well, in that case, we need to worry about this because as that array gets bigger and bigger and bigger, how is the time, the computation time increasing? If it's increasing like linearly, or, well, actually, I guess this would be like linearly. If it's increasing linearly, probably not a problem because, you know, you'll notice like for a very, very large array, it's not that much more complicated than it would be for a very, very small one. Whereas if it was like quadratic, well, forget about it, pal. You know, you want to get an array of that size, it's way off the page. So keep in mind, when we talk about like Big O, when we talk about time complexity, space complexity, we're not talking about how long something takes or how much space something takes up. We're talking about how the time it takes scales up according to its input. So if you increase the inputs, how much does that increase the computation time? Like if you double the size of the inputs, does that double the computation time, or does it quadruple it? Or if you double, let's say you quadruple the input size, but it only doubles the computation time. That would be more like a log n or something like that. Maybe, you know, ideally you've got this big O of 1, which is constant time or constant space, in which case you would say, like, you know, make that array as big as you want. Make the input as big as you want. It's not going to affect the computation time or the memory that this is going to take up. So that's ideal. But this is the part that I want to look at a little more now, because we've got data structures over here now. So we've got our arrays. We've been talking about arrays before, and we found that access, so like if you want to look something up like that array at I we were doing before, access is cheap. It's just big O of 1, or technically big theta of 1. I mean, this is sort of more big theta for the average, big O for the worst. That's one way of thinking about it anyway. We might talk more detail about like the big O notation and that kind of stuff in the future, but for now, I mean, you can think of it as average and worst. But so worst case scenario, or sorry, average case scenario, well, either one, for an array, it's going to be constant. You know, just look that up. You got it. You want the thing with index 7? Done. Here you go. Whereas if we need to search for it, if we need to actually go looking for it, well, now it's becoming more of a problem. And if you need to delete something, you sort of need to look for it, right? So that's becoming more of a problem. It's going to take a longer time. It's going to take a longer time to insert these things. And so that's why we would look at some of these other things, like a linked list, for example. So for a singly linked list, yeah, looking it up is going to take longer. It's no longer going to be free to just look up an element, because let's say we need this third element here. Well, we can only start over here. We can't just point directly to this. So we'd start here and then we'd say, oh, okay, maybe it's this. No, it's not that one. Is it this? No, it's not that one. Oh, there it is. Okay, we found it. So that's that's where index 3 is. That sort of thing, right? So it takes longer to get there, but inserting one, it's cheap. Deleting one, it's cheap. It's inexpensive to do either of those operations. So that's good, right? So there are trade-offs here, I guess is what I'm trying to say. Now, while we're here, we could take a look at the hash table. And the hash table is very cheap for all of these things, for searching, for inserting, for deleting. Why is there no access here? I think it's because hash tables are typically for unordered values. I think that's the idea here. But yeah, I wouldn't be able to tell you exactly. I'm pretty sure though, because they're for unordered values, so it's not like there's a sequence to them anyway. So when we're talking about access, we're basically talking about searching for them. So, okay. Yeah, we're using a hash table, that's good. And we're gonna put our singly linked list into that hash table. We're basically combining forces over here. So we should probably talk about linked lists. We should probably get an understanding of what a linked list looks like. And I have to say I'm really happy about this. I'm glad this is coming up now because we're up to this point, yeah, we've talked a lot about algorithms, we've done a lot of algorithm stuff, but we haven't actually done that much just straight up object-oriented design kind of stuff. So let's get some objects in here. That'd be fun. Let's just archive this for now, but we're gonna bring it back, I think. Or maybe not. Maybe we'll just, do something similar to it afterwards. So we want to make some objects here. So the first thing we're gonna invent, we're gonna make some new objects. If we haven't done this before, basically the way we make an object is essentially, well, okay, there are a few ways of doing it. We could use a class, but I've been told that class, the class keyword in ES6 is actually not good. Someone actually wrote a Medium article about how it's the most harmful thing in modern JavaScript. So that kind of scared me away from using class. Instead, we're going to do this in kind of an old school sort of way. So basically we're going to make the constructor. So the constructor, in other words, is the thing it's the function that we're going to call when we want to make a new instance of one of these things. So what are these things? Well, it's going to be called a list node, and it's basically going to have two things. So it's going to have a value, and it's going to have a next. And at the moment that we, well, actually, it's going to have both of those things, but we're not going to tell it what the next one is. When we make a new list node, we're going to give it a value. So for this, we'll say, no, not let. We're going to say this dot value is assign the value of value. Oh my God. That's a tough one. This dot next is assign the value of null. We're going to say there's no next to begin with. It's just going to be the value that it's going to have. So we could say something like let node be assigned the value of new list node, and we'll give that a value of 5. Okay? And then we'll say let next node also be a new list node, and it's going to have a value of -7. And then we'll say final node is going to be a new list node, and it's going to have a value that's just the word bye. And let's actually link these now. So we'll say node.next is assign the value of next node, and next node.next is assign the value of final node. So we're starting to link these things up. And then basically, what do we want to check here? Well, let's just return node for a minute, and we'll see what we get from that. And it's probably going to look almost like a little nightmarish. Let's find out. Yep, yeah, so it's a little complicated. It could be worse, I guess. But basically, if we take a look at what's in here, we've got, okay, so it's an object. It's in these curly brackets, or braces, as we sometimes call them. It's in the curlies, and it's got a value, which is 5. It's got a next, which is another object, something in between a new set of curlies. So, okay, what's that object? Well, it's one that has a value of -7 and a next of another object. What's the other object? Well, it has a value that's the word by, and a next, which is null, which means it's not pointing to anything. So if we think about it, I mean, this is kind of like, this is our linked list. Like this is basically like this thing over here, like our 1, 2, 3, except with 5, -7, and by. So that's another advantage to linked lists as opposed to a lot of arrays. Well, actually, we should talk about the advantages of linked lists. So let me pan over here for a sec. Oh, I love this new app. It's so great. Anyway, let's switch over. We'll switch colors, and I want to talk about memory for a second here. And again, this is like not my area of expertise necessarily here, so correct me if I'm wrong about any of this stuff. But from what I understand anyway, basically the idea is that when we're declaring new variables, when we're assigning them values and stuff like that, we're basically carving out space in memory. So we've got like our, I don't know, this is like a number line, but it stands for memory, and we say, oh, okay, well, here's our new variable. This is, you know, this is value. Let's just say. And then let's say we make a new array, and we're like, okay, yeah, we're gonna have this array, and it's gonna have like 5 elements, and so there's our array. Okay, and then maybe we insert some other stuff. We do some other stuff with memory. We've got like value 2 or something like that. So now we've got this other stuff, and you know, maybe other stuff after that. Okay, so basically the idea is we've got this array, and it's a fixed size, and if we want to increase the size, then we'd say, oh, okay, so you want like 2 extra elements on this? You know, yeah, we can do that. We can accommodate your request. There's enough space in memory here. That's fine. We can do that. Because I think, like, from what I understand anyway, the idea behind an array is that it is actually just a bunch of values that are sort of stored next to each other in memory. I think that's historically like how an array actually looks. And so then, since it has to be sort of like next to each other in memory, that means, well, we don't want to like split it across this thing over here. So if we need to increase this again, let's say, okay, I need 5 new elements. We would say, oh, okay, oh, no, we can't do that. There's value 2 over here. So, all right, listen, we'll accommodate your request. We'll take value 2, and we'll, can we move it? Yeah, let's move it like over here, or just like somewhere else, we'll say. And oh yeah, this app is so improved. I love it. All right, and then we say, all right, okay, we move that to somewhere else. Now we can add on that extra room over here. And now that's a bit bigger. So then we can say, okay, so then now we can put this back over here, I guess, like put this back in, but maybe we have to shuffle around other things. So like that's the sort of thing that could really take some time. So the fact that array values need to be next to each other in memory, from what I understand anyway, is sort of, that's why it's a problem. Like that's why, that's part of the reason it could take up like more, time complexity sort of thing. Whereas if we're not using an array, if we're using linked lists, then basically we would have like a node over here, node 1, and then we could have like some other thing over here, value 2. And then maybe we have node 2 over here. And the idea is that that's not a problem, because node 1 points to node 2, wherever it happens to be located in memory. And maybe node 2 points to something like way off into the distance over here. They don't need to be neighbors in memory, as far as I understand anyway. So again, correct me if I'm wrong about that, but I think that that's sort of at least part of the advantage of using a linked list. Let's get that off the page. Okay, cool. So that's basically what we want to do here. We're getting an understanding of our linked list. So basically, it's not exactly the same as an array. In some ways, it's better because it's a little more flexible in terms of how it's managed in the memory. But also, it has some advantages in terms of like the time complexity of inserting a new element and that kind of stuff. Anyway, we don't need to get too much into that right now. Main thing is I want to do something that's going to make this a little more efficient, I guess, right? Because doing all this stuff like on our own, it's kind of taxing. Like there's a lot of work to be done here. It's sort of like it feels a bit clunky, don't you find? And like the thing we get out of it feels a little clunky, doesn't it? So instead of this, we're going to make another object. And Actually, hold on. Before we do that, let's analyze this a little more. So this is what node looks like. But let's say we don't want just node. Let's say we want node.value. Can we just grab node.value? Is that okay? Can we just get its value? What should it be if we can? It should be 5. We get 5. Can we get node.next? Can we get that? Yeah, it's basically just the object that this one was pointing to. So the thing that had a value of -7 and a next pointing to this list node. Could I do something like node.next.value? Would that work? And yeah, it's giving us the -7. Or we could even do node.next.next.value, which should give us the word bye. Okay, so on that note, let's clean this up a little bit. So we'll say, all right, done with that. Now we're going to make a new type of object. So we're going to make a new constructor for this. And its function linked list. So we're going to make this one the actual linked list. It's going to start with nothing, as the argument. And basically, what are we going to do with this linked list? Well, we're going to have something called this.head. It's going to start out as just null. Normally, when we have an array, we sort of keep track of the length. So maybe we'll do the same thing here. So we'll say this.length is assigned the value of 0. I mean, there's nothing in this linked list, so it's going to start with a value of 0. Now, why am I saying head here? Why do we want this value of head? Well, basically, let's get a visual here. Actually, hold on. I don't want to do it here because I want to be able to flip back to it. So let's move away from this. We'll go back to it, but we want to talk strictly about linked lists for now. So, okay, pen, and yeah, basically we want something that works like this. Like this will be our first element. This will be like element 2. This will be element 3. And element 3 is pointing to like null, basically, right? It doesn't have anything else, so it just points to the end. And then we'll say this right here, that's going to be head. Okay, so head is always going to be pointing to this one. Why is that useful? Why do we want that? Well, basically just to sort of tell where the linked list is going to start. And we want to have a starting point because like there's no way we could just get directly to this if we didn't start with this one, right? So the linked list is going to start somewhere and then it's just going to be next, next until there's no next. So we're going to use head for that purpose. Now also what we want to be able to do is insert a new element. In fact, that's something we should be able to do cheaply, like without having to go to the end of the list here or like to check for it. So basically what we can do is, here we'll make a new element. So we'll say, ooh, new element, new, exclamation point. Okay, and then from there, we're going to say, so we got this new element, it's a list node, it's given this value. We want to say that its next is going to be whatever the current head is, whatever we have at the head right now. And then the head, well, we don't want it to point to the second element in the list, we want it to point to the first element in the list. So we'll do something like this. So now head points to new, and we can scratch that out. And now, just like before, we've got this linked list, it starts with head, now it has 4 elements, and it goes all the way to null. Great. Okay, so let's do that. So we're going to make a new thing here. It's going to be called this.add. Now keep in mind, just in the notation of objects, we would say that, or in the terminology, I should say, of objects, we'd say that these are properties, right? This.head is a property of each linked list. And when we say this, okay, hold on a sec. Let me Control X this for a sec and just back up to here. So I want to clarify what I mean by this. Okay, so when I say this, that's going to take on the name of whatever object we're instantiating here. So basically we're saying node is this new list node with a value of 5. So this.value is going to be 5, but only for when this is node. So that means node.value is going to be 5. And what we found before is node.value, yeah, it was 5. Okay, so basically that's the idea. This refers to whatever thing, whatever instance of the object we're talking about here. All right, glad we cleared that up. Let's move on from here. So this.add, now this is going to be a method. So we're going to have a function, and it's going to take in It's going to take in a value for now. Yeah, it's going to take in a value. And basically what we're going to say is essentially what we were saying before. So we want to make a new node and well, okay, it's hard to say whether we should handle making the new node here or whether, whether it should just be adding the value we want that node to have or whether it should be adding the node itself. So, yeah, let's make it add the node itself. That's probably just a bit easier to deal with. So, okay, I'll say this dot add is going to be assigned the value of function with an input of node. What's the output going to be, or what's it going to do anyway? Well, it's going to say node.next. So we've got this new node. Its next thing is going to be this dot head. So that's just taking the first thing we did here. We said this is our new thing. First, its next value is not going to be null. It's going to be this thing. Okay, so this dot head. Great. And then after that, we're going to say this dot head is no longer going to be pointing to where it was. It's going to be pointing now to node. And since we've added a new element, we're going to say this dot length plus plus. Yeah, thing just got a little longer. Okay, cool. So that's maybe going to make it easier for us to add elements to our linked list. You know what? I want to make sort of something. This isn't necessarily something we're going to keep, but it's just going to be a function called printout, or a method, I should say. And it's a function. It's going to take no inputs, and it's basically just going to make an array that's going to make this stuff easier to see. That's it. So let array start as that, and we'll say let node be assigned the value of this dot head, and while node, so while it's not null, we're basically going to say array dot push. And what are we going to push in here? Well, basically node dot value. Yeah, whatever the value of the node is. And then node, it's going to end up being node.next. Yeah, it's going to move on to the next one. Then at the end of this, we're just going to return our array. Okay, cool. So let's try this. We've got add, we've got printout, and notice this is taking node as one of its inputs here. So here, let's try this. So we'll say let node1 be assigned the value of new list node. Let's just give it a value of 1. And let node2 be new list node. With a value of 2. And we'll say node 3. Yeah, it's a new list node. It's got value 3. So we've got some nodes there. And instead of having to tie them and link them together ourselves now, let's just say let list be a new linked list. Keep in mind that constructor doesn't take any arguments, so we'll just leave it like that. And then we're just going to say, well, first of all, return list.printout. And that's a function, so we got to call it. It's appearing green. Hopefully that's not going to be a problem. Yeah, okay, great. So it's returning an empty array. Makes sense. There's nothing in the list. Okay, so what if we made it so that there was nothing in the list? Let's put some stuff in the list. So we'll say list.add node 1. Whoops. Yeah, let's just put node 1 in there. And yeah, now it's in there. Okay, list.add node 2. And yeah, now they're both in there. Now notice it's not really pushing these into the array. It's kind of more that it's unshifting them into the array, which we've seen before. Basically means it's just going to insert on the left at the head instead of at the tail. There are other ways we could handle this, we don't have to have head here. We could have head and then also tail at the end so that we could just put other elements at the end very easily. But I don't think there's any harm in inserting right at the beginning here. I don't think that's going to be a problem for us. So, okay, cool, nice. So that's list.printout. What about list.length? What should it be? Probably 3 now. Let's see if that aspect of it is working. It's 3. Okay, so this is great. This is really working the way we want it to. This printout function, like I said, it's not something we're really going to hold on to here, but it's something we're going to use for now. Okay. Anything else? there anything else we want to see on our linked list? Should we remove elements too? Let's remove elements too. That'd be fun. So we'll say this dot remove, and it's going to be a function, and it's going to take in an input of value. Okay, we're going to remove something that has a particular value. And, well, okay, what I should say is we're going to remove something that has a particular value if we can. That's sort of the goal. So how are we going to remove something? Well, first of all, let's just go back to what we had before. Okay, now let's say that we wanted to remove the 2. What ultimately are we trying to do then if we're trying to remove the 2? We're basically going to want to make the 1 have a next of 3 and the 2 have a next of nothing, so it's just kind of pointing to nothing, being pointed at by nothing, and just sort of floating around in space. Now my understanding is that there's a garbage collector that's going to pick up that kind of stuff, but again, I wouldn't say I have a very nuanced understanding of how all that stuff is working, so again, if anyone knows, let me know. Okay, so that's basically what we want. We want to say, all right, this element we're looking for, whatever the previous element was before that, make its next this thing's next. So the previous value's next should be this thing's next. And then this thing's next should be nothing at all. That's basically what we want to do. But that tells us we're going to have to keep track of what the previous element was, so let's start with that, I guess. So we're going to start with, we're going to say let node, well, that's going to start at the head. Let the previous value start as null, because at the head there is no previous value. And then basically, I guess we'll just go through it and we'll say, well, first of all, if node.value is the value we're looking for, if we found it here, well, actually that sort of means we're going to have to do something special, because that would mean it's the very first element here that we're trying to remove. And I think the way we would handle that is going to be a little bit different. So should we talk about that now or after? Maybe we'll talk about that after. So let's assume that that's not going to be the case for now, but we'll just leave a note here that says do something. Okay, great. And then basically for the else, yeah, that's where we want to do this thing. So we basically want to say, well, until you find the thing that is, so, well, first of all, let's say while node. So while there still is something here, okay, we basically want to be moving this along. So we'll say if node.value is value, then that's where we're going to remove it. We're going to remove the node, or at least we're going to do the set of steps we talked about over here. So we'll say the previous value is going to be, okay, so the previous value is next. Yeah, previous value is next is going to be assigned the value of this node next. And keep in mind, like, that might be null. Like, it might be this one that has a next value of null, but that's fine. That would just mean, like, you know, if we're trying to remove the 3, then the 2 should point to null, so that's not a problem. Okay, so previous.next is going to be node.next, and now we're going to say node.next is null. It's going to be pointing to nothing now. It's going to be floating in space. And then we're going to break, because we're going to say, you know, we found it. Don't go any further. We found it. And then otherwise, let's say this wasn't the one we're looking for. So keep in mind, this while node here means we're going to keep moving until we find the one we're looking for. So this is what we do if we do find the one we're looking for, in which case we're going to break. Otherwise, if we don't find the one we're looking for, then we're going to say, okay, well, now previous is going to be whatever node was, and node is going to be whatever's next. Keep in mind, if the node.next is null, then that means it's going to get to here, and it's going to say, oh, okay, null. Didn't find it. So this is where, like, we'll get to the end and we want to say, well, did we find it? Because we might not have found it, right? So actually, okay, let's say removed is assigned a value of true in this case, and we'll start removed as being something, it starts as false. Yeah, removed is false. And then at the end we'll say, well, if removed, then length minus minus, and it's not just length, it's this dot length. Okay, got to keep track of that, right? So just as we were incrementing length, we were doing a plus plus when we were adding a new element. If we can successfully remove an element, then we're going to do a minus minus on the length. Okay, so then there's really just one thing that's missing. It's this. We were saying do something. So what specifically do we want to be doing there? Well, basically, we want to be talking about the situation where we're removing this one, right? So in that case, we want the head to point to 2. So we want this one to be the head now. And so it's going to point to 2 instead of 1. And then 1 is not going to point to anything. So whatever the head was, break that link. And then whatever its next was, that's where the head's going to go. Okay. So basically, we'll say this dot head is going to be node.next. And then node.next is going to be null. And we're going to say removed. It's true. Yeah. And then I was going to say break, but like nothing to break, right? I mean, we've got the while out here. We're never even going to get to the while because of the else over here. So great. And then we have removed something, so that'll trigger the length minus minus. Cool. So does it work is the question. We've got, at this point, here, let's return, oh yeah, it was list.printout, I think, right? So let's get that running. See if we have any syntax errors. Okay, so at least this is working, but let's try removing something now. So we'll do list.remove 2. Okay, so if you've got 2 in there, remove that 2. So it was 3, 2, 1 before, now it's just 3, 1. So remove seems to be working. Does it work at the head? So can we remove the 3 and not have a problem? Great. Could we remove the 1 and not have a problem? Excellent. When we're doing this removing, is it properly altering the length? Well, in this case, yeah. The length is 2 because we added 3 things, but then we removed 1. If we want to find and remove the element that has a value of 5, well, now the length is 3. So why is that? Whoa, that's Control T, new tab. Sorry about that. Control R is what I meant to do. Okay, so that's why it's not removing anything. It's there was no 5 here, so it didn't remove it. Okay, no problems there. This is all great. So we can add new elements, we can remove elements, we can keep track of the length. This is working pretty good. I think this is doing sort of what we want it to do. I think we sort of have an understanding of our linked lists here, why we want to use them, what they can do for us, and I guess importantly, how we're going to use them. Because, yeah, that's kind of important, I guess. Now, at this point, if this linked list business is all good, if it's all making sense, and let's try to get a little more of that on the screen. Yeah, great. So if we're happy with this, if it's all making sense, then I think what we should probably start to do is try to optimize this thing for the purposes of our function down here. The file name, the thing we're actually trying to do in this task. So in a minute, we're going to take all this stuff and we're basically just going to copy it, paste it up here. Everything's going to be great. But before we do that, let's think about, ultimately what we want to change here, like how we want to optimize our linked list for the purpose of this function. And basically, if you think about it, what we had before with our hash values and all that kind of stuff, we had like these little arrays we were storing. Where'd that go? Was it here? Yeah, here it was. These little array things. So we had 3 things we were keeping track of. We sort of had the hash value or the key. We had the name itself, which starts as null, and we had sort of like this counter, the instances. So let's modify that then. So for the list, okay, here's what we're gonna do. So basically, let's move this out of here. Let's go back to this. So what we want is for a hash table to be sort of like this array, this moderately sized array that has elements in it which are gonna be linked lists. That's basically the idea. So every element of the array is gonna be its own linked list. Yeah, that's gonna be the idea. So, okay. basically we'll have a linked list here, or we'll start where we don't have a linked list here. We'll basically just start with a bunch of empty stuff, I guess, and then from there we'll put on these things. We'll put on these linked lists. But basically, what do we want to be keeping track of? Well, these, like within the actual hash table itself, we'll have like the index where they end up being stored. And so in the event of a collision, well, actually, maybe we could do this a bit differently. Well, okay. Basically, the hash value is in some way going to be stored in the hash table itself, like this big array, whatever we end up using for that. And then over here for each of these things, we're going to have a linked list. And basically the idea is that the linked list is going to store the name, like the name that we're looking for. And then also it should store the counter, like how the instances, how many of that name that we've seen already. So because of that, I'm going to modify this a bit. So I'm going to say this is going to have, instead of just value, it should be name and I guess count. Yeah, count. Okay, cool. So then not this dot value, we'll say this dot name is going to be name. And this dot count is going to be count. There we go. So our list nodes are getting a little bit different now. They're not going to look exactly the same. They're going to have a little more information in them, but that's fine. It's optimized for our purposes. And the linked list we're going to handle a little bit differently too. So first thing to note, we're not going to be doing any value stuff because, well, we're not going to have values. We're going to have names. We're also not going to be removing any elements, so we're not going to use this remove function either, which is a bit of a shame because, it was kind of nice. It took some time to build, but that's fine. Maybe we'll use it later, like for another task or something like that. And hey, look, if we learned something in the process, then it was worth it. All right, so at this point, let's make some modifications. So we're not going to do this dot remove. Instead, what we're going to do is this dot find. Okay, we don't want to remove an element, but at some point we will want to find an element. So I don't think we're going to need any of this stuff now, and we want to find it according to what its name is. So this is where we've already arrived at the right value here. We're saying, hey, that's my hash value there. Yeah, that's my hash value. Don't you take it? So if we're at the right hash value, or the right index, the right key, whatever we want to say, if we're at the right hash value, then basically the only difference between these things potentially is their names. So we want to find okay, so we know we ended up here, but did we were we looking for image or were we looking for doc1? Basically the idea is we'll arrive here and then we'll run through the list until we find the name that we're looking for. Okay, so that means this is probably going to be a lot simpler. Basically, we might as well just delete this stuff over here. Yeah. We want to find. This dot find is a function that's going to take in name. We're going to start at the head, and we want to say, well, basically this. While there's still a node, and while the name of that node is not the name we're looking for, then basically we're going to say node. Yeah, it's node.next. Yeah, just move on to the next one. And then if we get to the end of that, if it turns out that we didn't find a node, if we got to a point where node ended up being null, then that basically means, well, you went off the list. Your next here is null. There's nothing there. You went off the list. We don't want that to happen, right? And it probably shouldn't happen, but in case it does, then we'll say, oh, you know what? Yeah, you got me. Let's make a new node. So we'll say node is going to be a new list node because there should be one here that has this name. But if it didn't occur, then the count's going to be 0. There haven't been any of these yet, so we'll just make it 0. And then we'll just do a this.add node. Yeah, we'll just add it. We didn't find it, so now let's add it on. That's basically the idea. And at the end of this, we're going to return whatever node we did find, whether it was one that already existed or one that was there all along. That's sort of the idea behind this. So I'm going to start deleting this stuff because it's not really so much relevant to what we're going to be doing now. Let's see, is this all looking good? I don't think I see any problems with this. So cool. Yeah, okay, great. Let's copy this now. Let's get all this stuff from before. All right, great. And now basically the idea is we've got our list nodes, we've got our linked lists. So we've basically equipped this algorithm with these additional data structures that we can now use. We've built them, we can create them. And this, by the way, this sort of reminds me of something we've talked about before, this whole idea of monkey patching. Like if we wanted to do something like linked list dot prototype dot find is assigned the value of function name, like all this stuff. Like we could just take all of this and just put it right down here and it wouldn't be any different. That's a totally fine way of doing this. The idea is that we wouldn't want to do this sort of thing on an existing data type like array, like a built-in or something like that, because it might have unexpected consequences, as tempting as it is. Anyway, so but for something like this, no problem. If we want to multiply, if we want to modify list node or linked list, well, those are our objects, man. We made these. Okay, so we're not going to modify them for now anyway. I think they're working just fine. This thing is going to find the node we're looking for, and because of that, I'm inclined to make a few changes here. So the first change I want to make, well, okay, first thing I don't want to change actually is this. Our calculate hash, that's fine, not a problem. Nothing wrong with calculate hash, it's finding the right values, so I don't think that's going to be an issue at all. Now, in a minute, I might change this stuff up a little bit. I might change like how this is all working, but for now, I think I'll just do something like, let's just push something falsy. Maybe just false. Yeah, I don't know if that's really proper, but yeah, for now we're just gonna say push false. It's just all gonna be false. And then linear probing, I don't think so. We're not gonna be using linear probing anymore. That's the point. That's why we're using linked lists. So we're gonna go back to making find index, just what it was at the beginning here. Just this thing. Yeah, we're gonna go back to that, just for the sake of simplicity. And then, yeah, we're gonna make some modifications to this. Ultimately, like, there's gonna be some similarities here. It's not like we're totally gonna demolish what we had, but it's gonna be like, it's gonna be a little bit different. So let's see. Well, the main thing, like, a lot of this stuff is going to be at least similar in terms of how we're going to deal with it. Like we're going to take our name, we're going to give it a hash value, we're going to find the index. All of that is going to be pretty much the same. In fact, we don't need the name of this thing anymore. We just need the hash value. So yeah, pretty soon we might just get rid of that altogether. We'll find out. But anyway, what we do want, here's the thing, we want to be working with nodes here, right? Like these list nodes that we had at the beginning. So I'm going to write a function. Maybe I'll just clear this for now. Little placeholder, yeah, do something. All right, so what I want to do now is I want to make a function that's going to like find a node for us. Okay, so it's going to be get node, and this is going to take a hash value and a name. How are we going to do that? Well, basically, okay, wait a sec. Let's make an index for now, okay? For now, we'll just make it index. And basically, we'll say if hashTable at index. Do we have something there yet? And if we do, then we're just going to say, all right, well, in that case, if there's something at hashTable at index, like hashTable at index, like that would just start as false. Like all of this stuff is going to be false, right? And actually, okay, let's maybe not spoiler this quite yet. So yeah, we'll do something there. But first, what if it is false? You know, like what if there's nothing there? Like the way all of these things are going to start. What are we going to do with that? Well, basically, we're going to put a list in there. We're going to make it a linked list. So we're going to say, all right, well, let list be assigned the value of new linked list. And yeah, it's just going to be a list. And then we'll say, we're going to let node be a new list node. And what's it going to have? It's going to have name and 0. Boom. And then we're going to do list.add node. And hash table at hash, or at index, is going to be list. We're going to store our list there. And then we're going to return that node. Yeah. Yeah. Cool. And then over here, if it doesn't exist, you know, if there isn't, or sorry, if it does exist, if there is already a linked list there, then we're going to say return hash table at index dot find name. Great. So again, what we found before, hey, why is the indentation off? There we go. Okay, so what we found before about this find thing is either it's going to find the node that we're looking for and then it's going to return it, or if for whatever reason that node's not already in there, then it's just going to add it in there and then return it. So one way or another, we're going to get that node and it's going to be an element of that list. That list is now inside of the hash table. It's going to be at that, whatever that index is of the hash table. That's the idea. Okay, cool. So we find our index, we get our node. In fact, I'm wondering if we could sort of combine these functions. Maybe we should. Let's find out. So we'll see how it runs down here. So yeah, okay. Just to finish up with this though. So basically we have two possibilities. We start with this hash table, which is all just false, 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 false. And so then when we get to a point where we want to get a certain node, so something with a particular index and name, which, you know, I'm realizing, let's just make it the hash. Yeah, and let's just get the index here. So we'll just say let index be assigned the value of hash mod hash table length. Nice. Yeah, let's just do it that way, and then we won't need to do find index, I think. Hopefully. Anyway, yeah, is that good? Is that going to work? Yeah. Okay, I think that's good, because basically what we're doing here is we're saying we're giving a hash table, a hash value and a name. And the hash value is just what we get by doing calculate hash on that name. And so then we say, okay, I want the node. I want to find the node that corresponds to that one. So like just visually, if I was saying, I want the node for doc1. So it's going to say, okay, doc1, let's put that into calculate hash. So we'll run this function on it. It'll spit out some weird number, and we'll take that number and that value, we'll put it into get node. And get node will basically say, okay, here's the index of where it should be. We have a list there. What are we going to do with that list? Well, we'll go through the elements. We'll say, hey, is that doc1? No, it's not. Okay, go to the next one. Is that doc1? Yeah, it is. Let's return that node. And now you have the node you're looking for. Let's say we were looking for, what's another one? A or something like that, right? So we'll say we're looking for A and we find its hash value and we find, here's where it should be. So, okay, is this the head? Is this one A? No? Okay, is the next one A? Well, there is no next one. So we're gonna insert A into this one, and it would actually put it before doc because of the way, whoa, you can zoom now? Amazing. Anyway, because of the way this works, right? Like it's going to put it before, actually that's not quite what that was demonstrating, but what we saw before down there is what I'm trying to say. Like it's going to put it before the head. We're inserting at the head because we don't want to have like a tail pointer or anything like that. Anyway, the point is we're going to insert the node if it doesn't already exist. And if it does exist, we're just going to return the node that already exists there. Okay, so that's basically what this is doing. So we're going to say, does it exist already? No, it doesn't? Okay, we'll make a new list. We'll put in the node we're looking for. It has a frequency or a counter of 0. And yeah, frequency. Maybe that's what we should have called it. Guys, it's not too late. Let's do that. So instead of count, let's make it frequency. I like that a lot better. Yeah, frequency. And is there any other instance of count? Can we do a control F? Count. Okay, we're not finding it. All right, so let's see. Cool. So, all right, where were we? It was, yeah, over here. So basically we were saying, well, is it still a false or is there a linked list there? If it's still false, we're gonna make a linked list. We're gonna put in our list node with that name and a frequency of 0. We're gonna add it to the list. We're gonna put that list at hashtable at index, and we're gonna return the node because ultimately that's what this function is doing, getting the node. And otherwise, if there was already something there, then we're basically just gonna find the node. You know, we know where to look. We know the hashTable, we know the linked list to look in, and it's the linked list that's the one at hashTable index. Okay, cool. And then we'll find it, and we know that .find will be guaranteed to find a node. So one way or another, we're gonna find a node here. Cool. So that's gonna give us our node that we're gonna start with. That's sort of like our starting ground here. That's good. Okay, so let hash be assigned the value of calculate hash of name. Okay, so we're going to calculate the hash value of whatever this name is. That's harkening back to this over here, our calculate hash function, which we haven't seen in a while, but we're going to use it now. And then we're going to say let node just be assigned the value of get node. Get node of what? Well, hash and name. I think that's the way it's set up, right? Hash name, yeah, hash name. Great. So we're getting the node that we're looking for. What are we going to do with that node? Well, basically, we want to say, because keep in mind, this is a list node. So it has a name, a frequency, and maybe a next. Well, it has a next, it just might be a null. So what we want to say is if node.frequency is 0, okay? Is this the first time that we see this name? That's the question. And if that's the case, then yeah, let's do filenames.push, and we'll just put in node.name. Cool, great. Nothing more to be said if that's the first time we see it. Things get a little more complicated if this is not the first time we've seen it. So if the frequency is greater than 0, then we sort of need to be like, oh, all right, well, we're gonna have to modify that then. Oh, and by the way, keep in mind, like one way or another here, since we've now seen this thing, node.frequency, like we're increasing that. It's gonna get, it's one more frequent, you know, we've seen it one more times than we did before. So yeah, we gotta stack that up a bit. Okay, so this part is gonna look a little more familiar to the way we were handling it before. We're gonna say let new name. We need to find a new name if name was already stored in the array, you know, or in the hash table, I should say, like, and specifically in a linked list. But anyway, the point is, if we've already seen it, then we want to say, okay, so node.frequency, and then close it up. There we go. So our new name is the same name, but in parentheses, it's going to have the frequency of, you know, how many times we've seen it. And we know that that's not going to be a 0 because that's the only way we could get to this point. Okay, and then we'll say new hash. New hash is going to be just calculate hash and new name. Yeah, that's pretty much it. And new node, because it's not going to be the same node as this one, right? And, I mean, maybe it'll happen to be in the same linked list, but it's not going to be the same node. Each of these is going to be a separate node. Okay, so then we'll say new node is going to be assigned the value of, well, we'll call get node again, except what are we going to call get node with? It's not just going to be hash and name, it's going to be new hash and new name. Okay, there we go. Great. And then after that, we're going to do the same thing we did before. So now we have a new node. We basically want to say, well, until you find one that you haven't encountered. So while this is true, while new node.frequency is a non-zero number, we basically just want to iterate this thing. So we're going to say node.frequency, first of all, ++. Okay. Now that is the tricky part here. We're not saying new node.frequency, we're saying node.frequency. Because basically what we're trying to say is like, okay, let's take doc as an example. So we try to insert doc. And let's say we've already inserted everything up to this one. Okay, so we've got these 4 in there. Now we want to try to put doc in there. So we say, all right, so where's doc? Let's find where doc is. So, go through and say, oh, yeah, there's doc. So what's the frequency on that? Is it 0? Oh, it's not 0. Oh, okay, so we need a new name. So let's make it doc1, right? Put the 1 in there. That was the frequency, I think. And then we'd get a new hash value, new node. And so doc1, and we'd go and find doc1. And then we'd say, oh, actually, doc1 is taken too. There is actually already a doc1. It has a frequency of 1 if it's in there already. So, oh, okay. So in that case, 1 didn't work. We're going to have to repeat this, but now we're going to have to increase the frequency. So instead of 1, like it was before, because doc at 1, now it's going to be 2. And now let's retry this thing. So we'll try all of this. We'll basically redo all these things, but with 2. And again, we don't need the lets. And in fact, we shouldn't have the lets because that will mess with everything. Okay, so node.frequency plus plus, because we're using node.frequency over here. And also it's going to change that node.frequency in the actual linked list so that the next time we try to insert one, it's not starting again at 0, it's not starting again at 1. It's going right up to the value where we left off, and it's just incrementing it by 1, and everyone's very happy about that. And then after, once we get to the end of that, basically we want to say, okay, well, new node, not new name, new node, yeah, new node dot frequency plus plus, because we did find one, and then we'll put in the file name. So file names dot push new name. Okay. And I think that's it. So yeah, is that going to be it? Are we done at that point? Are we ready to give this a run? Should we test it out? There might be errors. There might be mad errors because we added a lot of stuff here. We're almost 100 lines in. All right, we might as well give it a try. We'll run the test and we'll see what's wrong. Oh, look at that. Nothing's wrong. Cool, so let's try submitting that. Perfect. All right, nice job. We got it done. We've gone on quite a ride here. We basically started, probably doesn't need to be that much space here. We started just with an array, just something simple like that. All we had at the beginning here was just an array. That was it. And it seems so foolish now, looking back at it, like imagining if there were 15,000 or 150,000 elements in our names array, this really would not be a wise way to do it. For the memory considerations we talked about before, for the inefficiency of using like a .includes or a .indexOf or something like that, we found that we got some improvements when we switched over to using an object. And the object, it started to get a little more complicated. We had to use object.keys and stuff like that. But that's nothing compared to how complicated it got when we got into this hash table business. So we started doing our calculate hash function, all that kind of stuff. We started using this linear probing, which we found was kind of a problem, or at least a potential problem, because it led to this clustering business. Now, here's the thing. As we ascend in complexity, and we started with an array, then we did just an object, then we did a hash table, it gets harder and harder to actually visualize these things. And I don't mean just in terms of looking at pictures like this. In terms of just printing this out, doing if we just have an array, we just do console.log, whatever that array is. When we get into the hash table, yeah, we can kind of do that, especially when we have linear probing. But now if it's all linked lists and stuff like that, that's getting a bit tougher. So maybe what we'll do is, if we want to see what it actually looks like, well, actually, hey, let's start with this. Let's, instead of returning file names, let's return the hash table. I'm curious about what it looks like. So, that doesn't look very easy to look at, I would say. So let's reformulate that a bit. In fact, let's just get this back in here. So instead of what did we have? It was this .printout, I think, right? I made the same spelling mistake last time. It's funny. So it's a new function, and how is this function working? Basically, it starts with an array, which is empty. We say let node be assigned the value of this dot head. We're starting at the head, and we want to say while node, basically array dot push node dot value, and node is assigned the value of node dot next. So we're moving on to the next node, and then eventually we won't have anything left, so we'll just return the array. So does that still work? Let's see. We'll do a hash table dot map, and list is going to get mapped to list dot printout. Will that work? Let's try that. Oh, list.printout is not a function. Why not? List.printout. Did we do something wrong here? Linked list. List.printout. Function. Return array. Why would it say it's not a function? It's saying it's line 106. Oh. Yeah, I know, because some of these are false. So, okay, yeah, if list dot printout. Yeah, actually, here, we'll do a ternary. So we'll say list dot printout, if you got it. And otherwise, I guess we'll just leave it as false for now. So let's try running that. Okay, great. It's not giving me the same issue for this one. Okay. What's the problem here? Oh, yeah, I know. There's no value anymore, so those are all going to be nulls. Name, that's what we want. So let's try that. All right, cool. Well, that's neat. So now it's actually giving us our sort of like a visualization of our hash table. And the visualization, it looks like arrays, what we have here, but technically these are actually linked lists. So it's linking to image, which links to doc1, which links to null, etc. Cool. Yeah, that's really neat. And so we sort of get an idea of like the clustering on this as well, I guess, a little bit, but we don't really need to worry about that anymore, because basically with the linked list, it's not like we're ever going to tell it to, like, you know, move to the next one or something like that. Okay, cool. So nice, very nice. Let's get rid of that last thing over there. So we'll bring it back to a point where it could run. And I don't know, should we keep the printout stuff here? I don't know if it's really worth it to put that in there. So maybe we'll get rid of it, just because, like, what was it, 106 lines or something when we had that in there? Now it's a meager 94 lines. That's nothing. Okay, cool. So I think I want this to be the official solution. Let's just see if there's anything that needs cleaning up here or anything like that. I guess we don't need two spaces there. Gotta calculate hash. Yeah, I think we're still using all this stuff. Oh, well, that's no longer relevant. That's not actually what we're doing. We're just making it false to begin with. Get node. Yeah, I think that's all good. Name of names. Guys, I'm happy with this. I think this is good. I think it's a good function. I think it's a solid algorithm. I think we've been on quite a journey today. We've looked at a lot of, well, at least we've looked at a few different data structures, some of their advantages, disadvantages. And the main thing is, what we hadn't really done a lot of before is really this hands-on working with objects, making new objects, giving them properties, methods. What I like about the linked list is it's basically an object used to manage a set of other objects. So that's kind of cool. You know, it's getting a bit hierarchical in here, a bit meta. So this is great. I'm really happy with this one. I'm glad we finished it up. Let's submit it officially. And there we go. Okay, great. Well, I think that's going to be it for this one. So nice job, everyone. You made it. Yeah, you did it. Give yourself a pat on the back. Good job. You earned it. All right.